Did it start? I'm assuming it started. Okay, there it goes. All right. Okay, so I'm going to start chapter 12 here, and that way you'll be able to view those two chapters separately. Chapter 12 is much shorter, so I'm hoping that I can complete chapter 12 by the end of Thursday. It only has about 5 different problems, okay? So chapter 12 is liquid solids and intermolecular forces, okay? So I guess we can talk about this. So in the space station, things just fly around in the air. So a floating blob in the space station, a floating blob of water is going to form a near perfect sphere because of those intermolecular forces, okay? So water, we're going to talk about the surface tension of water. And so on the space station, water would kind of hold itself together in a spherical shape, so it just kind of float around in a sphere. So you can see videos of this online, you know, of astronauts like drinking water out of the air and stuff. So the density of ice and liquid water are much larger than the density of steam. So obviously, water exists in 3 phases: solid, liquid, and gas. And it exists in all 3 of those phases at atmospheric pressure. So that's not true for all substances, but water is a very unique substance, and that's what provides us with life on this planet. So people are always looking for water on other planets to prove whether or not there was ever life there or the potential for life, because life as we know it is based on water and carbon, right? So those are the 2 things people want to look for. So notice that the density and molar volume of ice and liquid water are much closer to each other than to steam. So in other words, steam is going to take up a lot more space than ice and liquid water, and the density is going to be much less. Okay, so the density of ice is larger than the density of liquid water. Okay, so this is not the norm. Density of ice, not right. Density of ice is less than the density of liquid water. So there's an error here. I don't know why they said that. This is not the norm, but it's vital to the development of life as we know it. Why? Because the density of ice, okay, is 0.917. So I don't know why they got that error on here. It's 0.917, and the density of water is 0.998. Okay, so what does that mean? It means as water freezes, the density is going to decrease because of the crystal structure of water that forms here. It actually moves the little particles apart a little bit, and it means that ice is going to float on top of water. So if this wasn't true, our oceans would freeze from the bottom to the top. Instead, ice floats on the top, and that's why life can actually exist in the ocean in the frozen areas, right? So gas has a much lower density here, gaseous water, which forms a gas at 100 degrees C because that's the boiling point. Okay, so the molar volume of the gas is 30.6 liters per mole, and 18 milliliters per mole of liquid water and 19.6 of ice. Okay, so it's going to take up more room. Okay, so so the properties of the 3 states of matter, you guys know all of this from like 6th grade science. Okay, so gas is going to be a lower density. It's going to take the shape of its container, and the relative intermolecular forces are weak. Liquid water is going to assume the shape of the container that it fills, like it's going to assume the bottom of the shape of the container in this case. It's going to have a higher density. It has a definite shape, okay, but it's only going to assume the shape of the container as high as it fills that container, right? It has an indefinite shape, so it doesn't actually it has an indefinite shape because it assumes the shape of the container as high as it goes up in this container in this case, but it has a definite volume. So you don't change the volume of liquid water very much. Like that's why a liquid is used in the brake lines in your car, because liquids don't compress a lot when you press on them. If they did, then your car wouldn't stop when you pushed on the brakes, or we'd have to use something else for the brakes, right, other than a liquid. But liquids don't compress a whole lot, but if you get air in your brake lines, then when you press on the brakes, they're going to feel mushy because you got air in the brake lines, and gases actually can compress a whole lot. All right, so a solid is going to have a high density. It's going to have a definite shape, so it doesn't take the shape of its container. It's going to assume whatever shape it has. and it's going to have a definite volume. So it's going to have stronger intermolecular forces holding it together in that situation, okay? So liquids are closely packed, but they can move around a little bit. They are not very compressible, not like a gas, okay? And they're, they don't generally escape the container unless they reach the vapor phase, okay? So gases are more compressible, and this is because there's a large amount of space between the particles, right? All right, and so we talked about a lot of this stuff before, all right? And so they can be squeezed closer together. All right, so molecules closely spaced are not easily compressible, so like a liquid, but molecules widely spaced are highly compressible, like a gas, okay? So solids tend to have a regular ordered structure if they're crystalline solids, so like ice, like table salt. Amorphous solids don't have a crystal structure that's regular, so a lot of plastics are like this. Plastics generally are like this. What other amorphous solids do we have? I'm trying to think of something. Can't think of anything pure right now. Maybe they'll give us an example other than plastics. All right, so the particles in a solid are packed close together, and they do actually vibrate in place, so they are always moving, okay, but they're incompressible. So we talked a little bit about crystalline solids. Oh yeah, glass is also an amorphous solid, so it doesn't have a regular pattern over a long range. So glass and plastic. Crystalline solids are like salt and diamonds. They have a regular pattern. So when you break them, they tend to form sheared edges, okay, clean edges. So which state of matter is compressible? Obviously, that's going to be the gas. Right, so we can change the phase of something from, say, solid to liquid, liquid to gas, and this can be done with most substances, like even plastics. So plastics are going to have a melting temperature, and that's going to give you a characteristic for that plastic, and we have an instrument that actually does that. So solids melt and liquids boil when they're heated. The transition between liquid and solid can also be induced by changing pressure. Not everything actually has a boiling point or even a melting point. So a lot of substances will actually decompose before they reach their melting or boiling points, okay? So gases can be condensed by decreasing the temperature and or increasing the pressure. So when they're condensed, when gases are condensed, they're going to form a liquid, okay? So pressure can be increased by decreasing the gas volume, okay? And reducing the volume reduces the amount of translational freedom the particles have, so that will often result in a change of phase. And we're going to talk about that later on in this chapter. So when you heat a solid, you can often turn it into a liquid, and then you heat it a little more, you can turn it into a gas, okay? Or if you reduce the pressure, you can also turn it into a gas, okay? So then if you have a gas, you can increase the pressure or cool it to turn it to a liquid, okay? And then you can cool that liquid to turn it into a solid oftentimes, usually. That isn't always true, actually. So like liquid helium, we generally can't turn that into a solid because it's at 4 degrees Kelvin already as a liquid. So I don't think it's possible to solidify that. So when a liquefied propane tank is open, some of the propane gas escapes as gas, lowering the pressure in the tank. So what is that going to do? It actually has an effect on the outside of the tank. So if you open the tank and you let out some propane from the tank that's probably on your porch, then this is actually going to cool down, and that is going to be a result of evaporation. So evaporation is an endothermic process. It actually absorbs heat, and so that's going to cool the outside of that tank. And we're actually going to do some calculations later in this chapter with some stuff like that. So the molecular diagram shows a sample of liquid water. Which of the diagrams best depicts the vapor emitted from a boiling pot of water? Okay, so this is something I kind of want to point out to you, not so much because it's important, but because it's going to help you determine the way Pearson asks you questions. Okay, so notice the differences in these three drawings. They may not be immediately obvious. Okay, so I'm going to start on the right, and I'm going to go from right to left. Okay, so here we have oxygen is usually depicted as a red atom. Okay, hydrogen is usually depicted as a white atom. So if you get a little molecule kit, you'll have some red atoms in there, and those are oxygen. You'll notice that those have like 2 bonds, okay, because oxygen is divalent. And then the white atoms are hydrogens. They're only going to have 1 hole because the hydrogen generally only forms 1 bond. So that keeps your bonding pattern straight. So if you get one of those model kits, it'll help you figure this out, okay? So you'll notice that these are just atoms floating around. These are just atoms. They're not molecules, okay? So if you move over here to the middle, you'll see that we have diatomic molecules, okay? So we have H2, okay? And here we have O2. We have oxygen stuck together and hydrogen stuck together, okay? So here on the left, we've got hydrogen, oxygen, hydrogen. So this here on the left is our water, okay? So that's how you tell the difference between these two guys. It doesn't matter whether they're vapor phase or whatever right now. I mean, it's saying it's in the vapor phase, and this looks to be in the vapor phase because the water is not stuck together. But what matters most in this pictures as a comparison is that there's water on the left, hydrogen and oxygen in the middle, diatomic, and the atoms on the right. So you have to be able to understand what your diagrams are showing here to answer this question in Pearson, okay? All right, so the structure of particles determines the strength of the intermolecular forces, and we're going to talk about that in just a little bit. The particles are attracted to each other by these intermolecular forces, okay? And so these intermolecular forces determine the state of the substance at a certain temperature. The strength of these attractive forces is going to determine that state at a particular temperature, okay? So solids tend to appear that they're not moving, but even solids are going to be vibrating or whatever at room temperature. Okay, so let's kind of talk about what that means. So intermolecular forces can differ according to which type of structures you have. So we can have ion to ion intermolecular attraction. So what is that talking about? We're talking about we've got, I think I'm going to stop here in just a minute and we'll pick this up next time. We've got a molecule of water here. So we've got oxygen in the middle. We've got 2 hydrogens, okay, and these are covalently bonded. So the oxygen is covalently bonded to 2 hydrogens, okay? So this water molecule over here on the right also has an oxygen and 2 hydrogens. We're looking at it from the side, and it's covalently bonded to those 2 hydrogens. But the reason that oxygen sticks to itself in any phase, vapor, liquid, solid, is because we have an attraction between the 2 different particles. So that's why like dissolves like. You've probably heard that statement before. So we have a partial positive here on this hydrogen. We're going to talk about hydrogen bonding a little later on. And we have a partial negative on the oxygen. And that's because this oxygen is actually withdrawing electron density on the hydrogen. Notice the periodic table here. Oxygen is over here on the right. Remember, electronegativity increases as we go from left to right on the periodic table. So oxygen is actually the second most electronegative element on the periodic table next to fluorine. Now these noble gases don't really count. So oxygen is next to fluorine. Fluorine's the most electronegative. Oxygen is the second most electronegative. And because of that, the oxygen is actually able to pull electron density away from the hydrogen, leaving a partial negative on the oxygen and a partial positive on the hydrogen, okay? So what that's doing is it creates what's called a polar molecule or a dipole moment in the molecule. It creates a dipole between that oxygen and hydrogen. So the positive end of the molecule is this hydrogen here. It's going to be attracted to the negative end of the next molecule, which is water, the oxygen on the water. Okay, and that is actually called, in fact, it's called hydrogen bonding, but that's a type of dipole interaction. It's a type of polar interaction, and that is called hydrogen bonding. Okay, so we're going to continue talking about intermolecular interactions. Those are not the covalent interactions, but the interactions between molecules next time. Okay, so I'm going to go ahead and stop this recording. Okay, and we'll pick up this